First afternoon speaker is Konstantin Chetyrkin, who is a winner of the Frontiers of Science Award this year, and his talk about Multiloop Renormalization group.
I would like, from the very beginning, to express my sincere thanks and gratitude to organizing committee of that beautiful conference and to organizing committee for this Frontiers of Science for noting our work made almost 10 years ago. So let me start. Okay. So I would like to mention my colleagues, our joint collaborative team. I would sometimes call it Karlsruhe Moscow team. That team belongs me, Pavel Baikov, and Johan Kuhn. Here is propaganda slide, not very important, of course. And he is also a little bit more important because here is a result, which I noticed too late. Here should be one, also here should be one. Because for me, it is of some small importance, some counting Kamachi, you will see a bit later, that not beta 0, the leading of beta function QCD or just beta 1. Just that index would directly correspond to number of loops. So it means we computed beta 0, beta 2, beta 3, beta 4, and finally beta 5. Because, okay. Now, let me come to history almost by 40 plus years ago. I was working in Moscow Institute for Nuclear Research, and my good friends from essentially the same, graduated from the same Moscow University physical department as me, Volodya Belokor, Dima Kazakov, Oleg Tarasov, and Alexey Vladimирov. They started to investigate relation group in the group led by Professor Shirkov, the author of the famous book Bogolyub and Shirkov. In particular, they worked towards calculation scalar models, also in gauge theories. A bit later, my team not joined, but appeared, so to say, started their own project. It was Andrei Kataev, Fyodor Tkachев, who at that moment were just my diploma students. It was, the project was devoted to alpha S squared contribution to sigma total plus means to hadrons. It was first non-trivial contribution because to the alpha S, the corresponding diagrams are just QED diagrams, which were known for register already. So a lot of people were interested in what happens at first non-trivial order when already some gluon interaction vertex should appear. Because we all were friends, especially me and these guys, so there was a lot of contacts and exchange of ideas, in fact, long before the publication, which was extremely important for both teams and for success of both projects. Okay. So here, after some work and some exchange of ideas, and sorry, I was too fast, we published our work. Our publication was a little bit before because it is technically the same problem, but much easier because total number of diagrams is much less, for instance. And then they will publish this work. So it's interesting to know that our calculation, we were for that moment completely without any computers, so to say, because the very idea of computer algebra calculation was somehow new for us. So we did everything by hand, which was non-trivial, but was very useful, in fact. I would recommend to everybody from young students, young researchers to do something, not only with computers. And it was more complicated problem, so they were using already Schoonship, famous one. It was, I guess, one of the first application of Schoonship computer algebra system, the famous system created by Professor Veltman, the famous Veltman, for group calculation in QCD or in general for gauge theories. So both works have common features. First of all, we're all very young. Second, they were quite successful for a number of citations and for importance, I guess. And most important for future, that during fighting with complexities of the problem, because that it, nobody in fact knew how to do it properly, we discovered a couple of new approaches. This was polynomial technique in X space, it was our group, and that was infinite rearrangement, plus computer algebra Dubna group, which happened to be very important for future development of this direction of multi-loop relation group calculations, and this somehow eventually led to the 5-loop calculation beta function, which I will discuss a bit later. The reason of my appearance here, so to say. Okay. Now, in this talk, I will mainly discuss advanced method of relation group functions, and I will be mainly concentrate on methods based on massless propagators, which for me means P, I will call it P integrals, just massless diagrams which depend from only one loop, from only one external momentum, Q or the P. I should also say that the same method, Okay. I should also say that it is not only about pure beta function and purely anomalous dimension. Exactly the same are applicable to any two-point massless correlators and even to corrections in terms of expansion in masses. So that is a list of corresponding problems which could be attacked with, and which were attacked with that methods. In fact, as for purely renormalization group calculations, there is an alternative approach which will touch only a little, which is based not on massless propagators, but on a completely massive vacuum-ted poles. It has its own advantages and disadvantages, which I will discuss a bit later. So, because there is a word history in the title, let me start from some historical things. So, infinite rearrangement. It's a starting point of infinite reduction, which we'll discuss later, which helps us to kill one loop in calculation, say, of 5-loop beta function. Because when you compute 5-loop beta function, in reality, we compute only 4-loop P integrals. For 4-loop, we need only 3-loop P. So 1 loop less is much easier to do with. Okay, that is an example from simple example from 5-to-4 theory. If you like to compute this one, it is corresponding subtraction of subdivergences. So if you compute only that piece, then we set mass equal to 0. Then we have a trivial massless recursively 1-loop integral here, which are done in no time in terms of gamma functions. Now, you would like to compute corresponding term proportional to m squared. We should first somehow isolate the terms. Suppose the standard procedure is to differentiate it to m squared, because as we know, the corresponding counter terms in minimal schemes, which everybody is using now, are what to say, polynomial in masses, so to say, and we could do such differentiation. We could do it, but if we nullify the mass here, then we will have significant problems, because here the infrared problem, and the result of that will be wrong, so to say. If we put mass equal to 0, if we not put mass equal to 0, then it will be not wrong, but it will be more complicated to compute. Here, the most important idea is that one could change attach external momentum in this way and nullify this momentum. Then the corresponding diagram, because it is logarithmic divergent diagram, the corresponding result will not depend on either Q1 or Q0 or Q, and one can easily compute it in this form. And so the result will be correct. That is the starting point. It is quite useful, and I would say it's rather trivial. Now it somehow looks obvious, but 40 years ago it was not obvious so much, I would say. In fact, a few years after publication by Alexey Vladimirov, who invented the trick, there were at least one or maybe two other publications which reopened, rediscovered the same approach. Not always with references. Okay, that trick is called infrared rearrangement because we rearrange, in a sense, infrared that is low momentum part of our Feynman integrals, and there is in such a way that to make integrals simple to compute, and in such a way that not stop ultraviolet part. But because ultraviolet counter term which we're looking for is by definition depends only on situation when all loop momenta are very large and going to infinity. So it means that we don't, if we careful enough not introduce during that rearrangement extra infrared poles, then the result will be simple diagram which produce the correct result. But it's not always possible. This is the first diagram when it's also from 5 to 4 theory, but it's not possible because if we put our strong momentum here, then here there are two infrared problems, here and here, and we cannot kill it in one strike. Of course, one could put somewhere here small mass, but it will not go far because it will have now two scale. Relatively, now it's possible, of course, to do, but in more complicated case, it will be not so simple. So you should not add more than one external new momentum or more than one mass. Okay. Now the idea how to overcome the problem, which somehow related with Bogolyubov distribution approach to quantum field theory, is very simple. Instead, because two things: either you put here mass squared somewhere. It of course kills infrared pole, but it produces unwanted complications in evaluation of our integral. But if we just, because we know that problem comes only in Euclidean region sense, when p goes to 0, we should modify only a little bit small piece around p equal to 0, which is just enough to subtract the corresponding pole with formal delta function of p. You choose C in such a way that such combination would be infrared free for small p. It's very simple to do, and the result would be correct. And integration now could be done easily. So this observation led us to so-called R-star operation, which means that we generalize normal R operation to another R wave or R tilde operation in such a way that all infrared problems are removed with such kind of more complicated counter terms, but still the integrals which we are going to compute are massless ones and without any spoiling ultraviolet behavior of all Feynman of the counter term which we would like to compute. Okay. So I would like to say that there are when we apply this R star, if you do it by hand, it is always possible, but you cannot everything by hand, so to say. The algorithm is clear, but it's rather complicated. It's better to solve the corresponding combinatories, but that is not so simple. So it should be done on a problem-specific basis. For every particular problem, it is a separate problem. But now it's done for almost every almost every interesting problem. It's still under some development mainly related with works by a little bit me, but mainly by Amsterdam group. I mean, these people, who in fact also recently, for their purposes, discovered, elaborated on example beta function, very new approach to the R operation, which is called local one, which doesn't have any basically any combinatorial problems, but it has more demands for computer resources. Okay, so the main benefits from R-star operation is proof of the following statement, which already told once, that in order to compute counter term at the level of L plus one loop, one could reduce it to calculation of one loop less, that is L loop P integrals. So basically it means that calculation of ultraviolet counterterms is reduced to well-posed mathematical problem, which is called, namely, calculation of L-loop P integrals. So to L-loop problem, so one loop problem is to compute two loops, which is trivial. So two loops are trivial. Everybody knows how to compute one loop P integrals. The two loop problem already is not completely trivial. It was solved during our calculations at the beginning of 80s, after inventing and developing the Grimbar polynomial technique in X space. Now it's rather obsolete one because there are much more powerful approaches, but still it was useful at that moment, and even now sometimes it is useful. For instance, here I took a picture from this work. You can see that the authors were using Gegenbauer polynomial technique for calculation at 8 loops successfully, so to say. Now, when we go to 3 loops, so which means we would like to compute 3 loop P integrals. It is not Gegenbauer polynomial technique in X space is possible to apply, but is really not very convenient, and it does not really works very well. So the main breakthrough came with discovering of iteration by path method. That I will not discuss much because it's very well known now among at least people who are doing calculations with diagrams. Only some historical references, because at one loop it was used, but in the hidden form, of course. The important point is appropriate modification of integrand before differentiation. I mean, this here is multiplication by z difference of loop momenta. That was, in fact, was done first by Sasha Vasilyev, Yuri Pismak, and Yuri Honkonin, but in X space in a little bit disguised form. And that was done explicitly by Fyodor Tkachев and me and Tkachев. So here, general comments that by these days, after 45 years from discovery of that approach, it was developing very fast, especially the last, I would say, difficult to say, 30 years. And it is a very important approach which allows for every class of time integrals to reduce it to so-called master integrals, which usually not so many, which could be computed once and forever. And then you just a matter of reduction. So reduction is a big problem by itself, but it's also now under good control because people waste a lot of efforts to it. So, in fact, we will see how IBP relation reduction also important not only for reduction to simple integrals, but also to compute the very simple master, or not simple master integrals. As a result, I could only cite that citation from my friend Andrei Grozin from one of his lectures. Okay. With the use of IBP as 3 loops, the 3 loop problem was completely solved. And there was constructed the remarkable programs, 2 programs. Now the most important is 4 program Mincer. And before it was constructed written in terms of SCOON-SIP. And that Mincer was main tool for production of many interesting results. Here are most important ones. For instance, the first heroic calculation of alpha cube correction to E plus E minus by Sergei Gorishin, Andrei Katayev, and Serezha Larin. All were my former PhD students and diploma students too. But here it was really, again, a lot of, not everything was done by hand, but all preparation of diagrams to fit the computer was done by hand. All ultraviolet infrared counterterms were constructed by hand and fit to computer. It was really non-trivial to do because they also using at that moment at Dubna, in fact, these punch cards to do it. If you remember, if somebody in the audience remember what does it mean. No monitors, so to say. And somewhat later, I was able to repeat the same calculation, but now in general gauge and in automated way without any patch cards, so to say directly, but with, of course, with heavy use of mincer. So let me continue. So other more important results are real corrections to Bjorken, some rules for polarized production, and to the gross leveling Smith some rules, which were done by Larin and Vermaselen. In fact, here situation is a little bit simpler than for plus or minus or than for beta function, because here you direct compute coefficient functions using so-called method of projectors. And there are no problem. There are no infrared necessity to use any kind of infrared tricks. Then I computed completely automatic without any, completely with computers for loop work mass, anomal dimension for QCD, and a bit later, okay. Of course, in addition, I was trying a lot to compute for loop beta function. It was very interesting stuff, but I failed. In spite of all my efforts, then I was a little bit not so wise or whatever, but you cannot do it by hand. But automatic way, combinatorics was too complicated at that moment for me. I was not experienced. But at the same time, my colleagues from now, I would say also another Amsterdam team, which was somehow active in middle of 90s, also Sergio Larin, Timo van Rieberg, and Jos Vermaselen, they elaborated a completely new approach. When you set all the moment to zero, introduce a universal mass to all propagators, including gluon. It works. No thread problems, no control problems. The renormalization is simple, but not with Z factors. We should really understand how our operation works to perform renormalization here. And there is only one big disadvantage, that corresponding diagrams are really, say, 4 loops for 4 loop beta function, 5 loop for 5 loop beta function. So there is no that infrared reduction. And massive diagrams, even vacuum tadpoles, because eventually we're working with vacuum integrals, massive tadpoles, whatever. They are still very complicated because extra mass everywhere produce a lot of complication. It's possible to do with IBP, but it's not simple. But in this, it was really very ahead of its time calculation. It was repeated only almost 10 years, and confirmed only almost 10 years later, somewhere in the beginning of our century, so to say. Okay. And in addition, they also compute, of course, quark mass and normal dimension, and they computed in generic non-abelian gauge theory, while I computed only for particular QCD case. Now, here I would like a good idea to put the picture. I hope everybody here could recognize who is who here. It is Timo Jones. It is Professor Gross. It is Oleg Tarasov. It is Jos Vermaselen. Here it is 1 loop beta function, 2 loop beta function, 3 loop beta function. I mean, collaborators. And that is 4 loop beta function. Okay. So after eventually we started to think about 4 loop problems somewhere in the very end of 80s and the beginning of 0 years, first decade of our century. And it took us around 8 years. So the problem was IBP reduction, first of all. The reduction was done, in fact, without IBP, but with the help so-called 1OD expansion of the corresponding coefficient function in front of master. It was based on Bykov's representation of Feynman integrals and implemented as a 4-program mincer. I should say that now that one, I discuss it only because the very Bykov representation, which I will show later, is quite important now for general investigations of different properties of Feynman integrals and different properties of IBP reduction. By itself, that one of the expansion was the only available for us and for everybody, say until, I don't know, 2012, 2013. And it was important for us to have it. So the idea is simple, that every master in front of, because we have only everything is expressed in terms of propagators. So then the master is just function of only space-time dimension d. So a coefficient function in front of every master. That coefficient function is ratio of two polynomial in d. So if you know how to d one of the expressed polynomial, and you could collect many terms, 15 terms for it, which is not simple at all. It requires a lot of simple algebraic manipulations. You could restore, so to say, with some power of confidence, with some degree of confidence, the final result. So it was done by mainly Pavel Baikov using his new presentation, which is written here, which is interesting by itself, and now is a very important tool, but not for one-ODE expansion. But for us, it was extremely important. So now we have all technical means to do IBP reduction, so it means to perform, to solve follow problem. So we continue to the next level. The next level is calculation of E plus E minus, R of S, and deep sum rules at odd alpha S to 4. This was very interesting and important because it has led to significant reduction of theoretical uncertainties in the determination of alpha S from ZDK and especially from tau decays, because tau is has much less energy scale. And then we started to perform to 5-loop anomal dimension QCD. As a warming up exercise, we did quark mass normal dimension, which was not so complicated because essentially much less diagrams. There are somehow theoretically, I mean, the main reason behind is that when you compute final diagrams to quark mass normal dimension, you have only diagrams at worst with one squared propagators. I mean, people who are involved in IBP reduction know that propagators like 1 over P24, 1 over P26 are quite non-trivial to reduce diagram containing such propagators. So when you compute quark mass normal dimension, you have at maximum, if I remember right, 2 insertions eventually after all manipulations, 1 over P24 in different places. So it is not so complicated. But when you compute beta function, you have sometimes even 3 such pieces, such places in diagrams when you have these squared propagators, which makes very difficult IBP reduction. So it took us around 4 years eventually. Let me first discuss these some rules. So here's the main point, as I already told, that corresponding coefficient function are coming from corresponding operator product expansion. They are computed directly. They have been computed. These are results in numbers. They are not terribly interesting. But what is a little bit more interesting is that picture, which is a rather old one, but I like it because you can see here comparison, the effective and effective QCD, the Berkeley sum rule with experimental data collected at Jefferson Lab. So you can see here is alpha S squared, alpha S squared, alpha S to 4. Well, it depends how you look into that picture, but for me, it shows that how the corrections somehow help to bring theory and experiment in agreement. But some people don't agree with me. Okay. Now let me jump to the state of the art now. After, in fact, it's all transparency, 45 and 25 years since field 3 and 4 loop calculations of beta function, we know results for beta function and other, and quark mass normal dimension, and other if you want, ghost field and normal dimension from at least 3 different calculations. They all are in agreement, so we're completely sure the result is correct, which is quite non-trivial, in fact, because somehow in such calculations, everything could go wrong, especially with computers. Because, you know, I experienced a lot of things when suddenly computer inserted some wrong code inside of my code itself. Once per 1,000, or not, once per 2,000 diagrams. And it's very difficult to catch such things, but it happens, unfortunately. No, but most important that such problems are not repeatable. You cannot reproduce it. You take that, you find that particular diagram, wrong one, you run it, runs in seconds without problems on your local desktop. It's happening. So, okay, we were very happy that when everything was confirmed. Here is the result, just historical, because now it is available for general color factors, but for QCD you only need this, so I will not dwell much about it. There are some interesting features of this result. Namely, zetas. On general grounds, we could, because we know the structure of master integrals, in which beta function is expressed, then it means that we know that obviously that in general we have at 1 or 2 loops for normal dimensional beta function only rational results. At 3 loops we have rational plus zeta 3 plus such kind of structure should appear. Now, if you look into real result for beta function, you see that it is somehow there is a delayed appearance. There is no any irrational numbers up to 3 loops. At 4 loops there is only 1 zeta of 3. Oh, 2 zeta 3, but no, there is no zeta of 4. One could have even zeta of 5 here. I say at 4 loops. At 3 loops okay. Now same, I guess, somehow. And at 5 loops, we have again only zeta of 3, but for the first time we have zeta of 4. Okay. It was not quite clear why it happened, but it was a kind of interesting problem. And there's a related puzzle. When 25 years ago, Garishny, Larin, Kataev computed RFS scoop other functions, they also found there are no any pi squared or the same even zetas in the result. And it was quite amusing fact, and the author wrote that sentence. And in fact, this sentence, when we computed after 20 years next correction of alpha s to 4, it was the same structure, both for other function d4 and for corresponding coefficient in Bjorken Torres sum rule. We have all kinds of irrationalities, but not pi squared or no pi to 4. No zeta of 6, which in fact appear in every particular diagram. And relatively recently, we realized that the reason behind of it. And it immediately resulted to a number of, well, to my taste, very interesting mathematical relations. For instance, exact ones. At 4 loops, we have such kind of relation, which is valid in any one-charge model, not only QCD. Here, because we have it 0 for QCD, because the corresponding coefficient for not quite clear reason that we don't know why. It's just equal to 0 at 3 loop level. But at 4 loop level, we have such kind of factorization of coefficient in front of pi to 4. It's not all beta functions, only coefficient in front of pi to 4. It is expressed in terms of one loop coefficients and as it is, and coefficient in front of zeta of 3 in 4 loop coefficients. So here 5 loop, here we have 1 plus 4, again 5 loops. So it first means that even if we knew it before, we could predict it, that term, without any calculations. But unfortunately, we didn't know it before. We realized it a bit late after the calculation was done. I would like to show that that factorization is completely not trivial, because you can see it is for QCD, it is for Jane gauge theory, it is not obvious at all. In fact, using some consideration, which I will discuss a bit later, we could predict pi-dependent terms at any model at the loop level 4, 5, 6, and even 7. And it was checked in all possible ways, including 7 loop result for beta function in normal dimension 5 to 4 model, which was recently computed in a remarkable work by Oliver Schnetz. The reason behind that some special structure of master integrals, which I will discuss later. Okay, numerics I will skip, not very interesting. What is more interesting is, it is also skip. I would like to have a little bit more time. it is effective. We could compute effective due to so-called low energy theorem, which was discovered by us many years ago in collaboration with Bernd Kniele and Matthias Steinhauser. They look like here derivative with respect to m squared kill constant path, and so the result for C1 in effective Lagrangian of Higgs with two gluons depends on the logarithmical part of decoupling function. So it means it could be somehow reproduced using standard relation group considerations. It was done, and it means that we could compute one loop more. So that is we produce at 5-loop level, and here is a contribution from beta function, beta 5, which is important here. Well, okay, that's quite big one. Okay. When our calculation was, our result for beta function was published at that moment, just 4 days later, we got that email from Professor Gross, which was, of course, a great joy for us. Thanks to him. Then physical review letters also highlighted our publication as an editor suggestion. Now let me discuss in the remaining 10 minutes evaluation of how we computed 4 and 5 loop masters in one stroke and the related structure of pi-dependent terms. So that is my personal puzzle, which now is not puzzle anymore for any experts, but I was very young and not a big expert, so it was a puzzle because we knew that result for these 4 diagrams and we knew that result. At different diagrams, but results are very similar, only factor 4 for here and here. Now one could see that one could cut into different lines of vertices. One could, from that big diagram, to construct the 3 loop diagrams which were before. I mean, this one. In fact, all 4 diagrams could be computed as you cut a vertex in proper time or a line in proper place, or a line in proper place. Okay, here is how it's done. Now the solution is relatively obvious. If we cut, I suppose, by a line such a diagram and nullify all constant momentum, then we will have product of 3 loop diagram, one of which I have shown before, times trivial 1 loop integral with 1 mass. Such integral can be done in a very simple way. So with textbook formula, so eventually we come to generalization which is obvious now, so to say, but it was not obvious then, that glue and cut symmetry of matrix propagators. Here it's written here. So the point is that if we take a primitively divergent without subdivergences massless diagram, then every cut, every line of vertex produce 1 loop less propagator type diagram, and its value at d equal to 4. We find a diagram, so its value to d equal to 4 is just number. That number will be the same in no matter in which exact line you are cutting. So by itself, it's an interesting observation, but you don't know what to do with it. But then much later, we realize what we can do it, because now we understand why there are these 2 remarkable, or 3 in fact, remarkable relations in d equal to 4. We could reduce every of these 4 propagates to master. Here is going to master. Here are complicated masters, which here very simple masters, which could be complete gamma functions. And then we express complicated terms of, we take the equalities and express complicated masters in terms of simple ones. And the result will be that we will find complicated master in terms of trivial gamma functions, but up to some power on epsilon. But that is the same power of epsilon which we need in our calculations at 3 loops. Okay. So it means that it's working using glue and cut symmetry. You could construct non-trivial masters in terms of trivial watermelon integrals. So that was an idea how to do how to find for-loop master integrals. The idea is obvious. That is the corresponding master integrals. That is the most complicated ones. We take, by analogy, with 3-loop case, all general 5-loop diagram with 3 linear vertices. There are only 4 different graphs, every with 12 lines. We add proper nominators of mass dimension 4 to make the diagram primitively divergent without any infrared or ultraviolet subdivergences. Then glue and cut different in all possible lines, in all possible ways, and compose corresponding equations. Then we calculate all equations, reduce them to masters, solve them, expressing simple masters, complicated masters in terms of simple masters. And then we see what will happen. So that is how we did it. And in a remarkable way, we were able to compute all non-trivial masters in this way, in terms of complete trivial or semi-trivial masters. That is in terms of gamma functions. Here is the result, typical results which we obtained. And in fact, we cannot obtain all power, all series of epsilon square, but of epsilons in epsilon expansions. But it's exactly what we need to solve the follow-up problems. I mean, it means okay, exactly what we need for 5-loop calculations. Now there are remarkable features of it. Everything is taught in terms of this simple master, which in terms of which we express everything. What is important for future is that this is so-called after some looking into the result, we see that all pi squared proportional terms could be hidden inside of two combinations, inside only zeta of 3 and zeta of 5, and zeta of 7 as it is. So it means if you express your all mass in terms of these hated quantities, then there will be no trace of zeta of 4. That fact is not real because we have only three odd zetas, but we have, I would say, 28 masters. So it is not obvious from the very beginning that you can do it, but you can do it. And that is the reason, in fact, why the reason behind factorization of zeta 4 proportional term in beta 5, and it also led to many similar relations. And interesting to see that we also think then 15 years ago that the same way could be used for 5-loop master P integrals. It was very old transparency and 15 years old. And then recently the program was successfully implemented by these people. And they computed they found successfully all 5-loop master P integrals analytically in the sense of proper number of terms in epsilon. And in addition, so it means half of the problem of 5-loop problem is done, so to say, or almost half. For PP reduction, they used the so-called Laporte algorithm, which is called FIRE. In most remarkable way, all 5-loop master P integrals also could be rearranged such a way that to hide all pi-dependent terms within pi-independent ones. In addition, every pi-dependent contribution inside of pi-independent ones is odd zetas is suppressed by at least 1 power of epsilon. Here you can see how it looks. On the left, you can see hated stuff. On the right, you have how pi squared proportional terms are hidden inside. It is completely non-trivial, and it could be used effectively to produce a lot of model-dependent predictions for beta and gamma in any one charge theory, no matter which theory you have. Here is, in fact, reason of factorization because here is equal to 0 in QCD, that coefficient in front of zeta of 3 at follow-up QCD, at follow-up beta function of QCD. So that is this one. Okay, so you have a lot of them also at the level of 6 loops. And you can see that, say, 5 loops expressed in terms of coefficient only 3 and 4 loops or 2 loops, but not more. So on the left side, on the right side, you have all those terms by at least by 1 loop less, which means you could predict a lot of things. Okay. Now, Now we also were thinking whether glue and cut symmetry could be useful in general case. Of course, in general case, there is no glue and cut symmetry. If you just consider a diagram with mass, with many legs or whatever. No, nevertheless, one could try to use a weakened version, because if you have a completely finite integral, which could be checked without calculation by some morally simple power counting using Weinberg theorem or whatever, it must be finite reduction to masters, obviously. And then if you ask for the total sum after reduction of different masters on various masters times coefficient functions should be finite, you produce some, at least for sure, some constraints on the value of your masters. At first sight, let's check it. Let's forget about glue and cut symmetry, about these equations. Let's check for 3-loop level. No way. That is the only. It is finite, but you cannot do much probably because it's already mastered. You cannot reduce it, and okay. But what happens if we add one more loop? Again, don't use glue and cut symmetry at all. Only finite test. Then that is the original result. And if we don't use glue and cut symmetry, then we don't have this equality up to epsilon, and so that term will disappear. But this too will survive. So it means if you add one more loop, then for loop reduction of for loop finite p propagators produce all masters which we need for results for all masters at 3-loop level, which somehow means a kind of bootstrap. I never try. I didn't know any other examples when people were using this for something, but I believe it might be of some use for future. Okay. This is summary for master P integrals, which I don't want to read. I believe it's interesting case is glue and cut symmetry because in many other cases, almost every other case, people are computing very complete master one by one, usually. Here you compute everything by one calculation, so to say. Now, what about adding one more loop to all that stuff? Do we need one more loop? It is possible. Short answers would be we need it for better accuracy, especially for alpha S, for extension of alpha S from tau lepton and z decays, and probably we can do it at some point. We need 3 things: combinatoric of effect reduction. It is done because it doesn't depend on number of loops. It's not everything. Not all cases which are available is publicly available, so they're not published. But for most important things, for E plus E minus and for ZDKs, for propagators, they are available in public form. So they're very simple formulas. Now, 5-loop masters are analytically done in this work, as I was told. Now, practical solution for 5-loop problem, its reduction of 5-loop P equals to masters, is basically available mainly within so-called Laporte algorithm, which is very powerful these days, which is very actively used. There are many groups all over the world. And one of such group at least exists also in Moscow State University and led by Alexander Smirnov and his people. Now, let me come to conclusions. First of all, R-star plus Forcer. Forcer is a program which was developed by Amsterdam group, which was discussed by Takashiro in his talk. Very powerful program to reduce for loop P integrals. Means that 5-loop renormalization group functions are really doable, practically any model, but they basically all it is are done. But maybe there are some other models. Suppose not very long ago, people did 5-loop and 5-cubed theory, which also has some applications. Now, QCD, anomal dimension, and beta functions are done and very well checked. And the apparent convergence of perturbation series for work maximum dimension, and for beta function is quite good, and there are no real dramatic logical application of it. For future, I would say that 5-loop problem is partially solved. And I believe there are good chances that one more loop can be relatively soon added for such important problems as ZDK to hadrons and tau lepton to hadrons. All necessary pieces are already publicly available. What we need, this is available completely, it is available completely and published. And this is also, there are different, quite powerful teams with public codes for Laporta algorithms, so-called Laporta machines. They are improving steadily with every new calculation. I believe they already, to some extent, as we knew, because 5 loops propagators, 5-loop masters were done with the help of reduction of 5-loop p integrals. So already are capable to some extent to do 5-loop reduction. The only problem is that when you compute using glue and cut symmetry, you usually don't have square propagators. And real life, you do have square propagators inside of your p integrals, which complicates life enormously. But still, I believe it's possible. So I believe it's a very good problem. I mean, calculation of this for young, motivated researcher or researchers. As for beta function, I don't think it is really very important. It is, of course, much, much more complicated. So that's all what I would like to say. Thank you for attention.
Thank you for your talk. Questions?
So the GAC symmetry, what did you explain what is the meaning of this abbreviation?
I mean, I could come back. It's easy. So the point is that
Glue and cut.
glue and cut, exactly.
Okay.
You mean just
Yes.
language. Sorry.
Yeah.
Glue and cut, because if you have propagator and glue it with one line, because you have only two, you have vacuum diagram. If you have vacuum diagram, you cut in either line or in vex, you cut with artificial line to cut it, then you have cut diagram. Glue and cut. It's just a funny name.
Okay, no.
I would say now it's basically trivial. It is built in many other things and nobody inside us because it's trivial. But when 40 years ago, when people didn't have so much experience in multi-loop calculations, it was not trivial. It is for us.
Yeah, you did not explain the Gegenbauer method.
What?
The Gegenbauer polynomial method. Which
I don't understand.
Gegenbauer.
Yeah, Gegenbauer. Well, it is just spherical harmonics.
Spherical.
Yes, it is just Chebyshev. It was known before e equal to 4 Chebyshev. In d minus 2 epsilon.
D minus epsilon.
Да.
Okay.
Exactly. Sorry. It is just spherical harmonics, and they are not right normal ones. But
Okay.
X space is important because on the next space, if you have d equal to 4, then it was before very well known and used by Rosner, if you remember, very old publication by Rosner in 60s, at d equal to 4, because here you have this orthogonality relations when you integrate over angles to spherical harmonics. If they're different, they produce zero, so to say.
Yeah. So I had the impression that at the beginning you did not use the dimensional regularization, or did you?
No, we were always using it.
Okay, but later in the second half of your talk, the dimensional regularization was used.
Yes, it's always used. I mean, it is built in.
Okay.
MS bar, so to say, minimal, in a sense, it is built everywhere. You cannot do much without it these days. Maybe I should say it more explicitly, but it's somehow, it is our ground, so to say. It is like complex plane for mathematics. You can do a lot of stuff for real, but if you go to complex planes, you can do much, much more. And then come back, even though many integrals are done with.
What about the Wick rotation? Did you, I mean...
Well, the point is that what we're doing is relatively simple problems in some sense, because we always compute deal with propagators. Propagators, weak rotations is trivial. So there are no any kind of obstacles there. So you can either do it or don't do it, but in mind you had Euclidean integral. Of course, in more complicated cases, it's completely not the case, but simple case.
Concerning the sixth loop beta function, it seems the main bottleneck now is IPP reduction. Is that right?
Yes.
Just
Well, yes, I would say it is true. I would say the point is there is one small problem, so to say, that this the corresponding formulas for IBP reduction, for infrared reduction, they're not publicly available. Not because we are hiding them, but because it's really complicated, and with the moment we are not able to write a really long, clear paper about it. I don't know whether this local approach by Amsterdam group with local R operation is available, because here there is no problem with combinatorics. They already put in all combinatorics inside. But for sure, it will not be, it should not be used for 6 loops, because it requires much more computer power. So essentially, at some point, either we publish or somebody else would publish corresponding explicit formulas to rate reduction for beta function. Because for beta function, the only problem is Z3, gluon wave for renormalization constant. All other things are very simple, and also for rate reductions, corresponding combinatorial formulas are really very simple. The problem is that I was looking for many years, I would say, how to avoid gluon propagator in correlation with beta function. The answer is you cannot do it, unfortunately. It is built in somewhere. Because without gluon propagator, we would do it long earlier than what we did.
And another question is concerning this the no even power, even zeta numbers.
Yes.
If I think you gave explanation up to this 5 loop. Is that the true for all order, or it's so far
well,
only?
Let me come back. So the point is that everything is sitting in here. So if you have such kind of presentation, so when you have a result for your P integral, you have usually rational number, you put it aside, and you have some irrational number. And so irrational number usually either zeta or multi-zeta, multi-zeta, or even more complicated objects, some like that.
Yes.
And if you have such kind of representation, then the result which you obtain here, they are just coming from it in kind of obvious way, provided you have it. But you not always. First of all, here only for 5 loop case. In fact, for 6 loop case, we also have such representation. But the point is that it stops at some moment. Why it's available at all, I don't know. It is the effect of life. But if you could really hide your your pi squared terms, or the same even zeta inside of not even ones, then you could produce such kind of formulas. And it also should be more or less clear why we have such a fact that here on the left side you have 6 loops, and here you have only 1 loop less, at least everywhere. So we have some predictability. Why it is the case? It's because we have this factor for the epsilon everywhere, at least. So in some sense, for the epsilon, it counts as a loop. So for instance, let me come. This is suppose this is the most simple one. Zeta of 3 term in beta function appears when you have 1 epsilon in front of this zeta of 3 in masters. That will have this piece. But that will be like constant, then it will disappear. One more loop, you have 1 epsilon squared in front to have it in the result. But 1 epsilon squared from standard Hooft equation for poles, Hooft constraints. All high order poles are expressed in terms of first order poles. So that's the reason. So somehow these terms of order epsilon, they they save the situation. But that such kind of interpretation is not trivial at all. And in fact, it stopped to work, I forgot already, at least maybe at seven loops. You don't ask me why we don't know the all masters at 7 loops, but we know a lot of them to somehow to see what is going on. It stops to work. By itself, it's not very important phenologically, but why it's the case, there is a big piece of science of purely mathematics, which is called periods, which is the same like the funny name. Mathematicians like funny names. They call finite Feynman integrals, Feynman propagators, if you like, periods. So they study them and they understand. For instance, they have a theorem that z of 2 never appears in periods. I don't understand how they proved it, but it is fact of life. No z of 2 anywhere, as it is, so to say. Of course, z of 2 in front of z of 4, it appears.
Thanks.
Okay, let's thank our speaker again.